This lecture will cover the basic ideas in sections 9.1 and 9.2. Chapter 9 is where we talk about differential equations. When we talk about a differential equation, that's just an equation that has a derivative in it. And so you've seen these before, but we haven't really defined them. So here a differential equation is simply an unknown function and its derivatives. We classify differential equations in a variety of ways. What we're going to be concerned with here is the order of the differential equation. So the order is real simple. It's just the highest derivative that you see in the differential equation. And then whether the equation is linear or nonlinear. So when we say linear, that might be a little bit harder to understand. But basically, you're going to be looking at the function y and its derivatives. And as long as they're in the first power and they're not composed with other functions of y or its derivatives, so you're not going to see any products or quotient of y or its derivatives, then it's linear. If you do see that y or its derivatives are not in the first power or they're composed with products, quotients, and so on, then it's nonlinear. Let's look at a few examples to get the idea. In this first differential equation, it's a differential equation because you see the derivative y prime of x. So we have this differential equation. The first derivative is the highest derivative. So this is an example of first order. Now, is it linear or is it nonlinear? And in this case, it is linear. And when we're talking about linear, we're looking at the derivative or the function y and making sure that neither of those are in a higher power. So this has a 3y to the 1, so that's okay. And notice that we have the first power on y prime as well. And they're not composed with each other or composed with other derivatives or other functions y. So it is linear. I want to use blue. Let's look at the second differential equation. Y prime is equal to cosine of y plus 3y. The highest derivative is 1, so this is first order. Yeah, I like blue better. This is a case of nonlinear. And it's nonlinear because of the cosine of y. The function y is composed with another function cosine. So again, this is an example of nonlinear. Let's go to the next differential equation. Notice that this is a second order because we have a second derivative, and that would be the highest derivative in this equation. So second order. The question is this linear or is this nonlinear? And this is going to be nonlinear. It's nonlinear because of the y squared. Y is not in the first power, it's in the second power. So again, this is going to be nonlinear. I went back to green. Interesting. All right. Last one. This is first order. The highest derivative is a first derivative. And it may look nonlinear because you see the x times the y. This is actually linear. It's linear because y is not composed with y or a derivative of y. Having y times x is okay. Well, if it were y times y prime, that would not be okay. That would be nonlinear. Or if it was y times y, that would be nonlinear. But x times y is okay. It's still linear. And now that we sort of reviewed the order and whether a differential equation is linear or nonlinear, what we're going to do is we're going to solve a differential equation. So a differential equation is simply an equation with derivatives. And when you solve a differential equation, what you're trying to do is get back to the original function y. So typically what we have to do is integrate. In example 1, it says solve the initial value problem. So we have a differential equation. We want to solve it by finding the equation y and then use the initial conditions to find a specific solution. Again, how do we solve? We integrate. So if I want to go back to the function y, I'm going to take the integral of cosine of x plus 3x dx. So this is simply going back to what we did in calculus 1. But now we have a name for it. These are called differential equations. The integral of cosine is going to be sine. And the integral of 3x is going to be 3x squared over 2. So plus 3x squared over 2. And then we have a constant c. That's actually a general solution. Because of that constant c. So y of x equal to sine of x plus 3x squared over 2 plus c is the general solution to our differential equation. And now we're going to use these initial conditions that y of 0 is equal to 2 to find the specific solution to this initial value problem. So remember, that means that 0 is the x value, right? So we have x is equal to 0, y is equal to 2. I'm going to replace the y value with 2 and replace the x value with 0 to get sine of 0 plus c. And now when I solve that, sine of 0 is simply 0. So my c value is equal to 2. Now my solution is y of x is equal to sine of x plus 3x squared over 2 plus 2. This is the solution given those initial conditions, or in other words, the solution to the initial value problem. So if you're given initial conditions, you can find a specific solution. Or as an example 2, if you're not given specific condition, then the most you can do is find a general solution. In example 2, we want to find our general solution to this differential equation, and this is a second order differential equation. So that means that we have to integrate twice. To find y prime, or the first derivative, we have to integrate 3x squared minus 4x plus 6 dx. And that would give us x to the third, so 3x cubed over 3 minus 4x squared over 2, so minus 2x squared plus 6x plus some constant c, which I cannot solve for because I do not have initial conditions. Now to go from y prime to y, I have to integrate again. I'm integrating x to the third minus 2x squared plus 6x plus this constant c and dx. This is going to be x to the fourth over 4 minus 2x to the third over 3 plus 6x squared over 2, which should be 3x squared, plus c times x, plus another constant, I'm just going to use d. And that's the best I can do. This would be the general solution, which is our function y. Again, the solution to a differential equation is to go all the way back to the original function y. That's it for this section. Some common applications of differential equations would be gravitational fields, harvesting resources, looking at flow from a tank. If you'd like to see these applications, now for this summer course you're not responsible for those, but if you would like to look at those applications, then go into the Math 242 playlist and go to the 9.1 Math 242 video, and that would be the longer full-length video for the 9.1 section. And so what we're going to do now is we're going to move on to section 9.2. In the previous section, we saw that the solution to a differential equation would give us a family of solutions or general solution because of that constant c. And we would only get a specific solution if we had initial conditions. So how do we graph all the solutions to a differential equation, all the general solutions? How we do that is by a direction field, sometimes called a slope field. In this particular diagram, we have this graph, and you see all these little tiny dashes. This actually represents all the solutions to this particular differential equation that I have listed, which is y prime of t equal to y minus 2. And I'm only graphing it in the first quadrant where t is greater than or equal to 0 and y is greater than or equal to 0, but you could graph it in all four quadrants. But I'm not doing it for this particular example. So this is our family of solutions to our differential equation. These are all the general solutions. And it's going to give us the slope of the solution curve at any point t comma y. Look at the graph. We have, oh, I don't want it to be fat like that. We have our variable t for the horizontal axis, and the vertical axis is our function y. So if we have an initial condition, we can draw the solution curve, a specific curve at that point. Let's just say that t is 1 and y is 1. So we're going to have this point 1 comma 1. It's going to give us a specific solution to those initial conditions, and all I have to do to graph the solution is follow the dashes. If I were to follow these dashes, I would get my solution curve. Okay, so again, for the initial condition 1 comma 1, I have my specific solution curve. And you can do that with any initial condition. Find the point, draw the curve that follows those dashes. So those dashes represent little tiny tangent lines. And you can see that if the dash goes up, the tangent line has a positive slope, which is why we call them slope fields. If the dash goes down, we have a negative slope. And then also remember what the derivative is. The derivative is the slope of the tangent line. So each one of those dashes graphically represents the slope of a tangent line. Well, actually, they represent little tiny tangent lines, but they also represent the derivative at that point. All right, so some important things we want to note when we look at direction fields is we want to know where the derivative is 0. So when you look at our equation, our differential equation, and you set the derivative equal to 0, you would be solving the equation 0 equal to y minus 2. Or in other words, y equal to 2. Look back at this graph. Look at where y is equal to 2. It doesn't matter what the t values are, no matter what t value we choose, as long as y is equal to 2, the solution is a horizontal line all the way across the graph. So whenever that happens, it's what we call an equilibrium solution. So this solution is equilibrium. It happens where the derivative is equal to 0, and the function that goes with that, the solution, is y equal to 2. So think about that. It's the line, it's the horizontal line, y is equal to 2. If we take the derivative of y is equal to 2, we get a derivative of 0 because it's a constant function. And that's important because our equilibrium solutions are also called constant solutions. So y equal to 2 is an equilibrium solution, also called a constant solution, because the solution is a constant function. Why the equilibrium solution is really important is because when you look on either side of it, all of the solutions will either be going up or down. In the case where the little lines are going up, that means the derivative is positive, and it also means that the corresponding solutions y are increasing functions. If we look at any point above the equilibrium solution, let's just say that we're looking at the solution curve where y is 2.5 and t is 0. The solution goes up. Or let's go to t is equal to 1, and our y value is just above. Follow, and you have this solution curve. All of these represent some function y, and since it's going up, y is increasing. So again, if y is greater than 2, we say the solutions are increasing. And then when you look below y is equal to 2, you can see that no matter what point you pick, follow the curve, and the curve is decreasing. So when y is less than 2, we say the solutions are decreasing. So again, this is just some vocabulary. Something else that will come up with these equilibrium curves or these horizontal lines is in the case where the solutions are moving away from the equilibrium. So look at our graph. If we pick any curve, we can see as we go from left to right, all the curves are going away. They're all going away, 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 away from our equilibrium. So if all the curves are going away from our equilibrium, we say that the equilibrium is unstable. So an equilibrium solution that is stable would be the opposite. All the curves would be going towards the equilibrium solution. Let's move on to example 1. In example 1, we have these two direction fields, and they're exactly the same. They represent all the solution curves to the same differential equation. But if you look above the two different graphs, they have two different initial conditions. So all we're going to do here is just sketch the graph of a solution curve for each initial condition. So on this first graph, y is equal to, or y of 0 is equal to 2. So remember, and here our variable is t. So that says when t is equal to 0, y is equal to 2. Look at my graph, draw my point, and then follow. Ooh, this is kind of weird. And then just follow our little tangent lines. So that would be a graph of the solution curve given those initial conditions. And it's just a rough sketch, right? Let's go over to the next graph. Here we have t is equal to -1 and y is equal to -1. So -1, -1, looks like it's in third quadrant. And I will just go ahead and follow my curves. And that's it. Okay. So if you have a graph and you have some initial conditions, it's fairly simple to just sketch the solution curve. The difficulty comes here when you do have a differential equation, but you don't have a direction field and you have to graph it yourself. And it is important to see the direction field because that's sort of a big picture idea of what all the solutions will look like. In our previous example where we had that direction field and two different initial conditions, in that particular example there were no equilibrium solutions. However, if you are going to graph by hand, the most important thing to do is to find the equilibrium solution if they exist. In the case where they don't exist, life is going to get really hard because in that case, you're stuck with just putting in a bunch of initial conditions and checking to see if the derivative is negative or positive, and then just drawing a bunch of little tangent lines. So in the case where there is an equilibrium solution, and you can have more than one, then you know that on either side of your equilibrium solution, the graphs are either going to all go up or all go down. So most important, find your equilibrium solution. Once you've found your equilibrium solution, then the next thing you want to do is find where it's increasing and decreasing. Now in your book, they write this as two separate steps, but what I think is easier is just to go ahead and graph your equilibrium solution and then just do some test points. So you're going to be finding whether it's increasing or decreasing at the same time. So in your textbook, step 2 would be to figure out where you have increasing solutions. Step 3 would be to find out where you have decreasing solutions, which is fine. I'll show you what I mean in example 2. In example 2, we have this differential equation. Part A says, for what initial conditions, y of 0 equal to a is the solution constant, increasing, decreasing. Okay, so notice that in this particular part A, we're given that our t value is equal to 0. So it's saying when t is equal to 0, what y values are the solutions? Constant, increasing, or decreasing? Part B is to just sketch the direction field. And then in part C, sketch the solution for the initial condition y of 0 is equal to 1. Part D says, are the equilibrium solutions stable or unstable? Let's go to part A. I have my differential equation y prime of t equal to y times y minus 2, and I want to figure out where the solutions are constant. So the constant solutions happen when the derivative is equal to 0. And that just means I'm going to take y times y minus 2, set it equal to 0, and solve to get y equal to 0 and y equal to 2. Those are our constant solutions. Okay, so the constant solution is not the number 0 and it's not the number 2. The constant solution is the equation, because remember, the solutions to differential equations are equations. So the constant solution is when y is equal to 0, y is equal to 2. Now, I'm not going to find increasing or decreasing yet. What I'm going to do, and what I prefer to do, is go ahead and start graphing. I could graph in the first quadrant. I'm going to do the whole thing. All right. So I have a t-axis and I have a y-axis. And 0, 1, 2, 3, and I'll go -1 as well. So we can just assume this is 1, 2, 3, and this is -1. My equilibrium or constant solutions would happen when y is equal to 0 and y is equal to 2. So all I'm going to do is just draw all my little horizontal lines and draw in my equilibrium solutions, and I'm going to do my little dashes kind of over the t-axis because that's when y is equal to 0. Now that I have my equilibrium solutions, I'm not going to algebraically find out where my derivatives or differential equation is positive and where it's negative to find increasing, decreasing. I'm just going to plug in points. So for example, let's say that t is 0 and y is 1. Remember, in between those two equilibrium solutions, if one test point is positive, they're all going to be positive. So if I simply put in 1 for y in my differential equation that we have up here, it's going to be 1 times 1 minus 2, right? So we'll have 1 times 1 minus 2, and that's going to give me negative 1. That tells me my derivative is negative at that point. So if it's negative at that point, and here I'm going to just draw a little line going down. If it's negative at that point, it's going to be negative at all points in between those equilibrium solutions. So I'm just going to draw downward at that point, and I'll just fill in the other pieces going down. Again, this is just a sketch by hand, kind of forgive me. So that's the idea, and that's how I do it. So for example, if I want to figure out what the graph looks like above y is equal to 2, maybe I'll pick y is equal to 3. If we put that in our differential equation, we have 3 times 3 minus 2, which is 3. That's positive. That tells me that everything above y is equal to 2 is going to be positive, and I'll simply sketch that. Again, just a rough sketch so you can get an idea. Usually I start out not so steep, and then I just get steeper and steeper as we go up. Oh, now I'm getting really lazy and making these lines big. I'll just stop there. And the last thing I'm going to check is what happens when y is negative 1. When y is negative 1, I have negative 1 times negative 1 minus 2. So that would be negative 1 times negative 3 is a positive 3. It's going to be positive, which means everything's going to go up. And in the process of finding increasing and decreasing, I have also sketched my graph. So I do part A and part B at the same time. Sorry, getting really lazy and making these lines really big. Again, you just want to get an idea of what the direction field looks like. Let's look at the rest of part A. We were supposed to find where the solution is constant, increasing, and decreasing. Well, we found where it's constant, and by looking at the graph, I can see that increasing would be when y is greater than 2, also when y is less than 0. So y greater than 2, y less than 0. Don't know if you can hear the roosters back. That's my increasing. Okay, so where is it decreasing? It's decreasing between 0 and 2. So I would write that as 0 less than y less than 2. So y values between 0 and 2. That would be where I am decreasing. What else were we supposed to find? Okay, so we did A, and we did part B. We sketched our direction field. Now we need to sketch the solution for the initial condition y of 0 is equal to 1. So that just means I have a t value of 0 and a y value of 1. And I'll do that in red so it's easier to see. All I have to do is just follow and follow. All right, so that would be my part C. D, are the equilibrium solutions stable or unstable? Remember, stable means the solutions are going towards the equilibrium. Unstable means the solutions are going away. So if we look at y equal to 2, notice that all the solutions are going away from y equal to 2. In that particular case, this is unstable. Now let's look at y equal to 0. So that would be our t-axis. When I look at those solutions, they are approaching our equilibrium solution. That's an example of stable. So typically we use these types of graphs for logistic problems or population problems. So this is a little note down below. If you would like to view example of what we call a logistic equation, so this is a common application of our equilibrium solutions. If you would like to look at a logistic equation, then you can go into the longer YouTube video for 9.2 Math 242 in our playlist. Basically, these are population applications. A population is not necessarily people, it could be bacteria, it could be anything. And imagine if you had a stable equilibrium solution. Well, that tells you if you have an initial population below your equilibrium solution, since it's stable, that population will grow, 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 but it's going to reach a point where it sort of levels out, which is really important, especially when you're talking about things like bacteria. You want to know if it's just going to increase forever or if there is going to be some leveling out. Another example would be in an unstable solution where you can actually figure out where the population would decrease so much that it would die out. Okay, so that's it for this section. Bye.